more on 16-bit and 32-bit processor family, which is basically your 8086, 80286, 386 and 486. In length, we will actually discuss 8086 processor, but 286, 386, little bit as and when required, what are the differences, what are the similarities, we will discuss in that way. Okay, so what we are going to start with today is going to look into a little bit of architectural part of this 16-bit and 32-bit processor, and as a programmer, which part of this processor is accessible or is available for programmers to use, how we are going to use them to write our program. That is what we are going to discuss for this class. So basically your 8086 and 80286 are 16-bit processor. As I say, 16-bit processor, the basic idea till now we know that the size of a processor is decided by the size of arithmetic or logical operation the ALU can perform. That means 86 and 286 are capable of performing 16-bit operation, the operation on data set which are of 16 bits. Apart from that, 8086 have 20 address lines. A memory unit. How we define the size of a memory unit? I think down the slide, 2-3 slide, I have that as well. So any memory unit, we represent the size of a memory unit in terms of 2 to the power k cross m. Or some places it will be written as 2 to the power k cross n is the size of a memory unit. Yes? What do you mean by this? What is k and what is m? So as it is a memory, as we know, it have addressable locations. It is divided into addressable locations. We can say it have, if I have k address lines, then it have 2 to the power k addressable location, addresses. Yes? And each addressable location can have m number of bits stored in it. So the size of a memory unit is defined as 2 to the power k addresses, and each address is capable of storing m bit of binary information in it. So the size of my memory is 2 to the power k cross m. So here this k represent, if I say my 8086 have 20 address line, what will be the size of my maximum size of memory which 8086 can support? K is 20 means 2 to the power 20. Now next comes m. Here I will say 2 to the 20 is 1 mega. Now 1 megabits or bytes or nibble, it depends on how the memory is organized. Whether memory is bit organized, that means each address have 1 bit of information, or nibble organized, that means each address have 4 bits of information in it, or byte organized. What we are going to look into all these Pentium processors, memory is byte organized. Irrespective of data bus size, we will see what are the differences, what we are going to face if the size of your memory which we are considering and the size of the data bus is different. But at this point I will say all these Pentium processors are byte organized. Yes, so most of the cases this m will not be mentioned anywhere. That is why here directly, just knowing the number of address line, the size of the memory, maximum size of the memory which can be interfaced with the processor is written as 2 to the power 20 bytes. Because we are going to look into the memory which are byte organized. Byte organized means each single address is capable of storing 8 bit of information in it. Yes? So 8086 processor can have maximum of, or can support maximum of 1 megabytes of memory. And the last point which is shown here is about the speed of the processor. The speed of the processor is calculated in terms of instruction per second executed. Yes, so 8086 processor is capable of executing 2.5 million instructions per second. This is the speed of 8086 processor. Compared to 8086, 80286 is also a 16-bit processor. That means it is capable of handling 16-bit of data or performing operations on 16-bit of data. But architectural wise, it is different from 8086, and functional wise, it is very different from 80. Many advanced things being added to 80286. But in a simple way, if I compare 8086 and 80286, 80286 is also a 16-bit processor with 24 address lines. It has 24 address lines. 24 address lines immediately gives me, as the memories are byte organized, it gives me 2 to the power 24, which is 16 megabytes of memory space. So 80286 is capable of supporting maximum memory, which I can connect to the processor. 286 processor is 16 megabytes, and its processing speed is 4 million instructions per second. But both are 16-bit processors. The second, which I told that a little bit we will be discussing, is your 32-bit processor family. So under 32-bit processor family, we have 80386 and 80486. 80386, if you see, it have 32 address lines. So when we say it have 32 address line, the memory, maximum memory which it can support is 2 to the power 32, which is 2 to the power 30 into 2 to the power 2, 4 gigabytes of memory space. So if you see after 386, in case of 486, we have mentioned many features. So I should compare why 486 onwards only we started talking about this. Is our previous families up to 386, 8086, 80286, 80386 or any 8085, any previous versions of microprocessor were all fixed point processor. What is a fixed point processor, or what you mean by a floating point processor? Fixed point processor means it is capable of performing operation on integer values alone. Integer values only. Yes, I cannot perform addition of 1.25 with 1.35 or 5.5 with 3.5. That was not possible with the help of processor up to 386 family. These are all fixed point processor. Fixed point processor. Does it mean that we were unable to do any floating point or any fractional operation? No. We were doing with floating point operation for this processor with the help of a coprocessor. Yes, another coprocessor was designed which was supporting this processor 8086, 286 or 386 to perform any floating point or your fractional point operations. Like for 8086, we had 8087 as a coprocessor. 80286 have 80287 as a coprocessor. But after your 486 above, all the Intel family have inbuilt coprocessor present. That means this coprocessor, which are capable of performing floating point operation, was made a part of the processor. That is why it is written the floating point unit is internal to the 8086 and above processors. Yes. Otherwise, if you see address line, address bus is same as that of the 386 processor. So maximum memory to be interfaced are same. But the differences started from 486 processor is that it have internal coprocessor, or you can say is capable of performing floating point operation. These are floating point processors. Along with that, it had cache memory for the first time inbuilt to the processor, and its processing speed was 50 million instructions per second. We will look into as and when required little bit of differences. So all these processor, whatever we are discussing, as we have classified our instruction set architecture computers into two parts. One is your CISC architecture, another one is RISC architecture. We have seen the differences, the advantage and disadvantage part, but all these 86 family which we are going to look into are CISC architecture or complex instruction set computers. That means they do not have a limitation for storing or having their operand in an instruction. Your operand could be present internal to the processor or could be in the memory or external to the processor. So it makes the writing a program or programmer's point of view, it is simple, easy. But yes, of course, in terms of designing the hardware architecture, designing the decoder, it is complex. So this is the basic block diagram we discussed. I will go in little more detail. If you see this BIU part or execution part, I will go in little more detail of it, what we have, about what are the units exactly we have under BIU or execution unit. So I will be little bit in detail, I will discuss so that you can understand which are the part of your CPU, which as a programmer I am going to use, or which is available in the architecture. Architecture means all the units we have to show. But programmer's point of view, if you are looking to the model, programmer's model it is called, we will only highlight those registers, those part which directly programmer can use. So this is your complete architecture part, complete architecture of your BIU or execution unit. In the previous slide, I have shown that BIU is responsible, if you go to the back here, BIU is responsible for generating the address, which will be given to the address bus. And after reaching to that specific address, it may be your IO device, input device, it may be your memory. After reaching to that particular specific address, we look into the control signal, whether we are going to read or write operation. Then after verifying or after getting the information about read, memory write, IO write, the data transfer takes place. The data is available to the BIU, or data comes from processor to the device or from device to the processor. So, and execution unit is responsible for performing, executing the instructions. So if you look into detail, we have seen that your bus interface unit is responsible for generating the address. Yes, address generator. You have seen in the previous class I have shown that BIU contains an address generator. So how that address is being generated? So it has to generate a physical address. I have to go to a physical address in the memory or in the IO device, and either data transfer should take place. Either processor will send data to that location or processor will receive data from that particular location. So address generator basically consists of a set of registers which are called as your segment register. So BIU have a set of register. This is ES is your extra segment. It has some segment registers. First of all, I will say these are the registers. This up to this part, these are the segment register. IP is your instruction pointer. It is a pointer. This register put together responsible for generating a physical address. That address is sent, 20-bit address will be sent to the memory unit or to the IO device from where you want to fetch the data or fetch the instruction. Yes, so first we need to fetch the instruction. I have to send the address, and address is generated with the help of your address generator present in BIU. Address generator actually contains a set of registers. All these registers, remember, it is a 16-bit processor, and in this case my register size is also 16-bit. All the registers we are going to look into are 16-bit register. So these are a set of registers called as segment register. ES, CS, SS and DS are segment register. You have extra segment, code segment, stack segment and data segment. These are the segment registers, and IP is your instruction pointer. These are responsible for generating the address. If I want to fetch a, why these are different names are given, also I will explain. The memory unit, a complete memory unit, we are dividing it into different segments. What is the advantage of dividing? that also I will discuss. But at present, I will say that let us assume, as I said, my 8086 processor will have 1 MB of memory space maximum. Let us assume I have divided it into 4 parts. This division is very many types of divisions are possible. I am showing you a simplest one. Yes, and the first 256 KB I have reserved for your data segment, where I'm going to store my data. Data segment is used to store data. Then next 256 I have reserved for your code segment. Whatever program you are writing should be stored in CS code segment part. Whatever data operands we are storing should be stored in data segment. Then we have extra segment. Next 256K I have reserved for extra segment, and last 256 let us assume I have stored for stack segment. Code segment and stack segment have their own specific operation. Code segment is used to store the programs, whatever instructions we are writing. Assembler converts it into machine equivalent machine code and stores. Where it stores? It stores in the code segment part of your memory, physical memory which you have connected to the processor. Similarly, data are stored in the data segment part of your memory. Stack segment, I will come in detail when we are going to use this stack pointer or stack segment. Yes, and whenever you go for string operations, we generally use stack segment, and extra segment is you can store anything into your extra segment. Yes, so these are the physical memory. This is my memory unit, external memory unit, which I have assumed to be into 4 parts. Now, each of these parts, this will have a 20-bit address line. That 20-bit address line is generated with the help of these registers. If I want to generate an address for data segment, I will use data segment register with IP to generate a physical address for data segment. If I want to generate, first I want to fetch the instruction. That means I have to go to code segment and fetch my instruction. So I will be using CS register with IP to generate address and go to that specific address to fetch the instruction. Yes. So this is how basically we generate, or your BIU has some register which are called as your segment register and a pointer to generate a physical address, and from that address we fetch the instruction. After fetching the instruction, as I said, what we do, the control signal will be generated whether we are doing read or write operation. In this case, it will be read operation because I am fetching an instruction. So instruction, that machine code will go to this particular address, and as the instruction control signal is read, this data, whatever available bit of data or data will be transferred to the data bus, will be given to the data bus, and it will be available to the microprocessor BIU part. Now the whatever you have fetched should be stored somewhere. I have shown you instruction register is a part of BIU. Here we are writing it as an instruction queue. Yes, whatever you have fetched will be stored in the instruction queue. 8086 have 6 bytes of instruction queue. The size of the instruction queue of 8086 processor is 6 bytes. It can store 6 bytes of data. It is not instruction, 6 instruction, no. One instruction may have 8-bit of machine code. One instruction, you have seen different types of machine codes. If I am writing add a comma b, what will be the size of the machine code? 16-bit. If I am writing add m1 comma m2, it may be 32-bit or even more, 64-bit. Yes. So my instruction queue available with 8086 processor is a 6-byte instruction queue. That means I am capable of storing 6 bytes of data in an instruction queue. It may be a single instruction, it may be multiple instructions, depending on what is the size of the machine code generated by that particular instruction. But 8086 processor is having 6 bytes of instruction queue. Yes. Let us assume I have one instruction which is of 2 bytes and another instruction which is of 3 bytes. And then next it will wait, it will not fetch any instruction. After fetching these two instruction, the processor will not fetch any instruction until and unless this data has been transferred to your ALU part and the memory is available, because minimum we need 16-bit or above size of the space to store at least one instruction, the minimum size of a machine code. Yes. So here the instructions will be fetched and stored in the instruction queue, and your ALU will or your decoder will take those instructions byte by byte and process them. Yes. Instruction decode. As soon as it moves to instruction decode, again your BIU will generate next address from where it need to fetch the data. So fetch the instruction. So by this process, having instruction available in instruction queue, execution unit does not have to wait for an instruction to be fetched to process it. As soon as it is done with this instruction execution, it will immediately go to the next instruction and start executing it. The execution unit do not have to wait for fetching of instruction. So instruction queue helps us to keep the instruction ready for execution, and BIU and EU can work parallelly or simultaneously instead of waiting for each other. Yes. So after the instruction is being given to the control and timing, which is responsible for generating the control signal as well as instruction decode, the operands are being fetched. If operands are internal, then they will be processed. If they are not internal, they will be, again we will be using, the address will be there in the instruction where the operand is present. As I have shown, if it is a memory location, I am specifying the memory address. So that address again will be sent through address generator. We will go to that specific address in the data segment, fetch the data operand and make it available to your ALU. Yes. And then your ALU, those data will be stored into the temporary register. Here we have a set of temporary register. This is your AX register, AX, BX, CX, DX, and BP, SP, SI, and DI. The detail I will discuss again in down 2-3 slides. But here, these are the 8 registers. These all registers are again 16-bit registers. These 8 registers are temporary registers, part of your execution unit. Any operation I want to do, the data need to be stored within the processor to perform the operation. So we will, whatever data, even if it is internal to the processor, it will be somewhere in this register. If it is not internal to the processor, we will fetch the operand and bring it to some of the register and operate on it, and the result will be generated. The result will also be available in one of these registers, and then if you want to store it externally, you have to send it to the some memory location or some output device. Yes. So here we have again a set of temporary register which are 16-bit register, and in this again we have some classification AX, BX, CX, and DX. These first four registers are called as general purpose register, and the rest are having a specific operations. I will tell you what are those specific operations. So the only thing here we have to understand is these first 4 registers, which are general purpose register, you can store anything on it, and basically used for any operation. We used to keep our data on it, process, and then generate the result, store the result. These 4 registers can be broken up further, can be broken up into 2 parts. AX register can be broken up, it is a 16-bit register, can be broken up into 2 8-bit register. One is the lower 8 bit are called as AL register, the upper 8 bits are called as AH. Lower byte you say and higher byte. H stands for higher byte, lower byte. Yes, 16-bit of data. So I have 2 bytes of data here. The lower byte is called as AL and the upper byte is called as AH register. So if you have 16-bit of data, you can use AX register directly. But if I have 8-bit of data, Then if I want to store 1 to H, my data is 1 to H. So if I use AX register, I write AX is equals to 1 to H. Actually, it will store 001 to H in AX register, because when you are writing AX, it is 16-bit. It is processor will understand it is a 16-bit data. Even if you have written only 2H, AX is equals to 2H, it will append with zeros and making it AX as 0002H. Yes? It will be treated everywhere by the processor as a 16-bit data, not to 4-bit data or 8-bit data or any other size. Yes? So the processor has given a flexibility that if you do not need, you are not handling, it is a 16-bit processor, but you are not handling 16-bit data. You are handling 8-bit of data. Yes, then instead of wasting this much of space, we can break this register, these 4 general purpose registers, into 2 parts. One is your AH part and another is AL part. Each of these sub parts are capable of storing of 8-bit of data, and they can be treated separately. Microprocessor will understand if you are writing AL is equals to 1 to H, it knows that AL is a 8-bit register and the data stored on AL is 1 to H. If you are writing AH as 102H or only 2H, it will understand that AH is a 8-bit of register, so it will append 10 and it will make it 02H. But when you are writing AX as 12H, it will make it as 0012H. Hope it is clear. So this general purpose register, this first 4 general purpose registers can be broken up into 2 parts. Each part can be treated separately as a 8-bit register. So if you do not have a 16-bit of data or you want to operate on 8-bit of data, instead of wasting AX or using AX, we can use AH or AL. Flag register. There is one more part present, which is a flag register. The flag register is also a register for a specific purpose. It shows the status of many different operations. Now we are using ALU. Many operations we are doing will use arithmetic and logic operation unit, and some of the operation instructions will not use ALU. Yes, and whenever we are using ALU, the result generated will be the status of the result. I am adding +5 with -5. My result is 0. 0 will be stored somewhere. Along with that, the status of this result will be shown with the help of this flag register. The 0 flag will be high. The 0 flag will be raised. The result is 0. Result is positive. Result is negative. Overflow has taken place. All these informations are expressed with the help of flag register. So we will go into detail of these registers now. So before that, I have taken this one slide just to revise, which I have already done. 8086 processor, as we said, have 20 address lines. The address lines are named as A0 to A19. It has 16-bit data line or 16-bit data bus. 16-bit data bus means it is capable of transferring 16-bit of data at one clock cycle. Yes, it can transfer 16-bit of data from microprocessor to the IO devices or to the memory, or can receive 16-bit of data from memory device or IO devices to the processor. So data bus size in this case is 16-bit data bus named as D0 to D15, and some control signals. Majorly, we will look into 4 control signals. One is memory read, memory write, IO read, IO write. As I said, these control signals tells us whether we are performing read operation or write operation. And externally, I have connected either memory or IO devices. So I should tell whether I am reading or writing onto memory or reading or writing onto a IO device. So based on that, generally we have mostly 4 control signals, which are memory read, memory write, IO read and IO write. So these are the signals generated by the 86 processor. And we know based on the address bus size, the memory is organized. This we have already discussed, whether it is ROM or RAM. The memory, Intel family, the memory is byte organized. So this M, I am going to fix it to 8 bits. You need not only address line is given, you should be able to write what is the maximum memory size the processor can handle, because whatever memory we are going to discuss here is byte organized. Yes, so here it is shown as ROM. So ROM is read-only memory, is capable of only, we can read the data from present in the memory, we cannot write. So here that those control signals are not shown, and address lines we will have as it is 86 processor. If I am considering, my address line will go from A0 to A19. Data bus will go from D0 to D15. And the data bus you can see is coming out from the memory, only read operation. It can only transfer data from memory to the processor. Data bus is not bidirectional here. Yes? But if it is a RAM, I will show data bus like this. This is as well as this bidirectional. I can microprocessor can send data to the memory. Microprocessor can read data from memory. And along with that, we should have a control signal to specify whether you are doing memory, MEMR, memory read, MEMW, memory write operation. So that will be in case of RAM. So as I said, the maximum size of the memory which 8086 can support is 2 to the power 20, that is 1 megabytes. So how I am going to express this 1 megabyte of addresses? 2 to the power 20 addresses we have. So the first 2 to the power 20. So 20 bits, binary bit representation. In hexadecimal it will have how many digits? How many digits in hexadecimal? A0 to A19. I have address A0, A1, A2, A3. This first 4 bit will give me one hexadecimal digit. Yes? A4, A5, A6, A7. Next hexadecimal digit A8, A9, A10, A11. Then A12, A13, A14, A15. Yes? Then A16 to A19. How many hexadecimal digit I will get? 5. One hexadecimal digit is equivalent to 4 binary bits. You know how to convert binary to hexa, hexa to binary. Yes? So as we have 20 address line, A0 to A19, we will have our, so 2 to the power 20 combinations. It will start from 20 zeros to 20 ones. So first 20 zeros will give me 0, 0, 0, 0, 0. H. 2, then it will be 0, 0, 0, 0, 1. It will start up and it will go up to all ones, 20 ones, which will be F, 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 H. This is the address space. This is the maximum address space a 8086 processor can have. Yes? 0, 0, 0, 0, 0 to F, 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 F. This is the address space. This is my first address and this is the last address possible in case of 8086 processor, as it have 20 address lines. Yes? And this memory space we have actually divided into different segments. I will come to that. So this is just a comparison slide where 8086 and 8088 are being compared. 8086 and 8088 both have 16-bit processor, but the basic difference, or more or less, they are quite similar. 8086 came first and then 8088 came. Why? Because now if you look into the architecture of 8086, I will come here. The memory is byte organized. Yes? But I have an address bus of 16 bit. So if I have a memory unit here, which is byte organized, yes, byte organized means each one memory location can have how many bits of information in it? 8 bits, and your data bus is 16 bit. So at one particular clock cycle, when I want to read this address, it will transfer 8 bit of data. It will not transfer 16 bit of data. How I will read two addresses then? If I want to use my microprocessor properly use, I have 16 bit of data bus, but I am only, my memory is byte organized. It is not matching, yes? My memory is capable of sending 8 bit of data or receiving 8 bit of data, but my microprocessor is capable of transferring 16 bit of data. So this was a little trick here. I will show you how memory is organized. Yes, memory is byte organized. Your processor data bus may be different. So how you are going to transfer 16 bit of data or 32 bit of data in case of 386 and 486? Your data bus size may be 32 bit of data bus. How you are going to transfer that much of data when your memory is not supporting that? So we will look into that, how it is being done. But this was the conflict, that your processor is capable of transferring 16 bit of data, but memory, in one memory location, I have only 8 bit of data. Yes. So 8088 was proposed saying 8 bit of data bus. Simple. I have 8 bit of data bus, my memory is byte organized. So in one clock cycle only, I can transfer 8 bit of data only. I will go to one memory location, read the data or write down to that. So my microprocessor and memory was synchronized in terms of size of data they can handle. That is what 8088 did. It simplified, but what complex solution we have for 8086, I will discuss this a little later, not at this point of time. And then the second difference was the instruction queue. This is a very minor difference. 8088 had a 4 byte of instruction queue, whereas 8086 had 6 bytes of instruction queue. The major difference was this data bus size. 8086, though proposed capable of handling 16 bit of data, my memory was not supporting. So some solution was taken later on stages that we will discuss. So I will stop here. In the next class, again, I will go in detail what are these segment registers we discussed. Some of the registers are present, are the part of BIU. Whoever is part of BIU is responsible for generating address. Some of the registers are part of your execution unit. They are responsible for handling the data or some other operation. So what are those operations? We will look into detail in the next class.